All right, gang, here we go. This is for Physics Unit 9. Unit 9, Part 3. We're talking about, in this video, it's the second half of Part 3. We're talking about capacitance. All right, so in the previous video, what we talked about was this idea of electrical potential and how we can kind of think about electrical potential in a very similar way to how we think about gravitational potential. Electrons, just like things, want to fall to the ground because they'll have lower gravitational potential energy. Electrons will want to fall down a wire in order to have less electrical potential energy. Okay, and so we've finished off last video by talking about batteries, so on and so forth, and how they kind of hold their potential in the state of chemical potential energy. All right, and so here, just to kind of start us off here, we've got a battery, right, and it's attached, and we've got a positive and negative terminal. We don't really know which is which in this case here, but so it's some battery, and it says it's a 6-volt battery, and they've got it connected to two plates, and so we see there's no electrical connection between these two plates, and so there's not going to be a complete circuit here because the air between them is a very poor conductor. All right. You could imagine that if in between these two we connected a wire, and this wire was connected to a light bulb, okay, that we could have, like, here's my light bulb. See my light bulb. All right. And this light bulb would get lit up, and the energy would come in one side, light up the light bulb through resistance, and then go out the other side, right? And so the same kind of idea occurs here. Now, the interesting thing is, without this light bulb in place, we actually get an interesting phenomenon that we're going to explore here called capacitance. All right, so a capacitor are two plates that are electrically neutral, okay, and they're close together. They're usually parallel, although they don't have to be. The easiest ones are parallel, okay, and so we've got this capacitor right here, and notice there's no net charge. There's an equal number of negative and positive charges on both sides, all right. Now what occurs is if we close this switch in order to complete this circuit, electrons will flow from the high voltage to the low voltage, just because they're going to a lower potential energy, right? So they'll go down here, and what will happen is the electrons will actually get built up on this plate, and then through induction they'll push these electrons down and away towards the other side. So we can kind of see this in progress from left to right as we go across these graphics here. This is the same graphic we just looked at, and then here in part B, the switch is closed, electrons are coming up, and notice how that they're building up, and now there's less electrons here, they're getting pushed off, because pretty much by that idea of induction, right? It's completing that circuit. And then, and so while this is occurring, we're saying the capacitor is being charged, okay? And then after once you've reached this point where it's done charging, the voltage here, or the potential difference between these two plates, of the plates, okay, this will be equal to the potential difference on the battery, okay. And so the capacitor's potential difference is going to be equal to the battery's potential difference. All right, and so once that occurs, your capacitor stops being filled. All right, and so you could imagine that if we, took a light bulb again, and we broke this wire and stuck a light bulb in the middle. Let's just say we did that real quick. So we got a light bulb. All right, here's our light bulb. Here's the filament. All right, so there's our light bulb, and then we connect it. So pretend this line's not there. And then we do the same thing here. Here's the same light bulb, okay. All right, and there's that. There's the filament. Okay, there's that. That wire's not there, right? It just goes into the light bulb, and then this guy over here. All right. Light bulb, filament. Nice. All right, no wire. All right, and so you could imagine, well, what would occur with our circuit here? In order for this light bulb to light up, we need electrons to pass through it. All right, it's kind of the sneezing tree way of thinking about this. All right, so electrons here, there's no electrons flowing through it, so our light bulb is not going to be lit up. Here, though, we do have electrons flowing through it, so we are going to have our light bulb lit up while the capacitor is charging. Once the capacitor is charged, notice that there's no more electrons here to get pushed off. Okay, where there are probably electrons, but they're not. But our potential difference has reached a point where it's no longer lower potential energy for them to fall. So our light bulb has stopped being lit. Okay, so capacitors are interesting because they only allow the circuit to be complete while the capacitor is being charged or discharged. When the capacitor is completely charged, the circuit is not complete. All right. So we can use capacitors to store charge. Okay, and essentially what they're doing is they're storing electrical potential energy for us, kind of like a battery, but slightly different. All right, so we can measure this amount of energy that it holds, and this is called capacitance. And this is really just a measure of its ability to store charge, and it's equal to the charge divided by the potential difference. All right, the charge on each plate divided by the potential difference, and the units, the SI units for capacitance, is the farads, and we use a capital F for that. So and then we ask the question, it says, in what ways is a capacitor like a battery? Well, it's like a battery that they both store electrical potential energy. Okay, both store electrical potential energy. Now the difference is with a battery, okay, battery, it stores it via chemical energy. All right, like like a AA battery, 9-volt battery. These are just chemical reactions, redox reactions that are waiting to take place. They just need a place to send their electrons. So by completing the circuit, we're allowing them to complete that circuit, and so the electrons can travel. So batteries use chemical energy to store this electric potential energy, whereas a capacitor, it stores it as just in the electric field. The energy is in the electric field. All right. And so really what occurs is that a battery's ability to release its energy is really, in a way determined by how fast can its chemical reaction take place. Whereas in a capacitor, electric fields are photons, or, they're electromagnetic waves, right, is a way to think about them. Electromagnetic waves travel at the speed of light. Right, so a capacitor can, no matter how much energy it's holding, it can release that energy really, really, really quickly compared to a battery. All right, so that's one of the big differences is how they hold it and then how fast they can release that energy. All right. So here's another way of looking at the capacitance formula, okay, and we've just taken these guys and now we're looking at it in terms of the permittivity. All right, this permittivity value right here, this guy is a way of quantifying how easily the electrons can travel in between these two plates. All right, that's the permittivity. Capital A is our area and D is our distance. So now we say, how would capacitance change if the metal plates had more surface area? Well, if the metal plates had more surface area, that means our capital A would get bigger, so our capacitance would get bigger. All right, and then next one says, how would it change if they were closer together? Well, that means that D value would get smaller, so we're dividing by a smaller number, so overall this guy, the capacitance, would get bigger. All right, and this just explains it. Here, what they've done is they've taken our two values for C, these two formulas, that guy and this guy, set them equal to each other and solve for Q. So we can use this to solve for Q between a capacitor without actually having the capacitance. Kind of handy. All right, now, so far we've just looked at capacitors that are pretty basic. It's just two metal plates separated by air mostly, ideally a vacuum. All right. Now that is a really simple capacitor, but they're not very effective. They don't hold a lot of charge. So one way we can make the charge of a capacitor work better is by using what's called a dielectric. And remember, die means two, and electric means it's got charges. Okay, and so by using a dielectric, what we're doing is we're introducing a substance between the plates of our capacitors that can have both charges. Okay, and so here, this is our negative charge, so this is where the electrons are flowing into this way, and this is where they're flowing out of, down here. And so what's happened is we've built up this negative charge, but we've induced a charge on this dielectric. All right, and so dielectrics are, really any insulator would be good. So they've listed rubber, waxed paper, air. Okay, all these guys are good dielectrics. All right, just anything that is a good insulator. So by putting an insulator in there, what we can do is just, it's increase the amount of charge it can hold, because now instead of just holding charge here on each plate, it's also holding, that charge again on the dielectric. And so if you break open a capacitor from like a circuit board, you'll actually probably see it's full of like usually white stuff that's really just kind of like paper or plastic confetti, more or less. All right, so those are dielectrics. They increase the capacitance. They increase how much charge can be held. Lots of different capacitor applications. All right. Whenever if you have two plates and you touch them to each other, then it will discharge it. So flash attachments on cameras use capacitors, right? So if you've ever used a disposable camera, hit that little button to charge it. You can actually hold it up. You can hear it go wee when charge up when it's winding. it's winding, and that's the flash that's charging up. Okay, and it wouldn't be very good to have a flash that just kind of went like a flashlight. You want something that really goes whash. That's the sound they make, so that they make, so it really brightens up your picture, because it's not going to be very helpful to make your picture look better if your flash didn't go off all at once. All right, and then some computer keyboards, like the fancy mechanical keyboards like gamers use, these use a lot of especially the old school ones, use capacitors in order to create the circuit. All right. And they would look something like this in this picture right there. All right, last little bit here. It's energy and capacitors. So this is connecting what we talked about last video with this video. This is the potential energy due to the electric, or the electric potential energy, and it is equal to 1/2 Q times delta V. All right. And so essentially what we can do is we can relate these two values together. All right. We can figure out, well, how much charge or how much work can we be doing, or how much potential energy is stored in our capacitor. All right, and we can really use this and the formula we used before to solve for all sorts of things. So if we didn't have Q value and we only had our C, then we could plug this guy in for our Q, and we'd get 1/2 C times delta V squared. Or if we didn't have delta V, we could plug this in, and so we'd get Q squared over C. And you'll find that as you work through the rest of this unit, that this kind of math happens all the time, where you've got like 2 or 3 equations that all have similar values, and you can kind of plug them into each other in order to solve it. All right, so let's do a practice problem, then we'll be done. It says a 225 microfarad capacitor is connected to a 6-volt battery and charged. How much charge is stored on the capacitor? How much electrical potential energy is stored on the capacitor? So we've got a capacitor, so that's our C value, and here's our voltage, so this is our delta V, and charge. How much charge is stored on the capacitor? So we can use this formula here, Q equals C delta V. All right, so our Q value equals C times delta V. So our C value, that's our farads, 225, and it's micro, so let's say that's times 10 to the minus 6 farads, and then times our delta V, well, that's just 6.00 volts. All right, so we say 225 times 10 to the minus 6 times 6. Oops, 225 times 10 to the minus 6 times 6. And we get let's see, how many sig figs? 3 sig figs, so 1.35 times 10 to the minus 3rd. That's what they got before, I got earlier. 1 times 10 to the minus 3rd. All right, and it's Q, charge. Charge starts with C, so that's coulombs. All right, and it says how much electrical potential energy is stored on the capacitor. All right, well, in order to use this, we're going to use our new formula. This guy right here, PE electric, is equal to 1/2 Q delta V. All right, and now we have our Q value, we have our delta V before, so our PE electric is equal to 1/2 Q times delta V, right? Unless I forgot it. Okay, good. All right, so our Q value is what we got before, so that's 1.35 times 10 to the minus 3rd. Oh, I forgot the 1/2. 1/2 coulombs times our delta V, which is our 6.00 volts. All right, so we take our answer times 6 divided by 2, and we get 4.05 times 10 to the minus 3rd, and it's energy, so it's joules. All right, so that's that. Next part here, we'll talk about current, then resistance, and then straight on till morning. All right, so do your practice problems. Try to, keep track of all this stuff. This stuff can be pretty tricky, so make sure you're really thinking about it. Those practice problems will help you a lot. Try to wrap your head around it. All right, do let me know if you have any questions, and I'll see you on the flip side.